Hello, my name is Joe Lane, and I'll be talking today about using ArcGIS and LiDAR data to do paleotopographic reconstructions. This is not an entirely new idea. This is kind of an inspiration I got from this paper from Hauk et al. 2017. It's new insights into regional scale mapping and modeling of the Paleozoic succession in northeast Alberta. So this area, if you ever heard about Alberta tar sands, this is kind of a hot spot for it. They have a lot of data, a lot of borehole data that they can use to map down into the subsurface and create this, what they call a subcrop map, or in this, they're using it to reconstruct the paleotopography. So taking this idea to another area, Alabama, and specifically looking at the northwestern corner, the Highland Rim is what it's called. There's a lot of geographic diversity in the area, and we'll be focusing on that. We don't have a lot of borehole data, but what we do have is kind of the same idea. They're mapping these different geologic units, the Cretaceous, and I think they're the Devonian, but we'll be looking at the Mississippi. So there's the Mississippian is about 300 million years ago. Cretaceous is about 100 million years ago. So there's this huge divide in time, lots of time for things to change. And so we're taking these green units in the Cretaceous, comparing them to the blue and purple in the Mississippian, and we're going to map that Cretaceous, see if we can kind of do some kind of paleotopographic reconstruction from the contact of those two time periods. So we went to the national map with the USGS to get our LiDAR data. They were in point cloud. LiDAR point cloud is there available in this LAZ format, which is a compressed form of the LAS dataset. So we got those files and we decompress them using LAS zip, and then to convert them into LAS files. The reason they are compressed is they're quite large. From this, I had almost 90 gigabytes of data once they're all decompressed. So they're compressed for a reason. Went into ArcGIS and created this LAS dataset, and then used that LAS dataset to create a raster in ArcGIS Pro. From there, we imported that raster into ArcMap, and then used this from the Alabama Geological Survey. They had mapped out the contacts available and geospatial data on their website. So we went back and mapped these contacts units in this feature class to create these polynomials. And from that, you can extract by mask from that LiDAR data, or from the raster that we created from the LiDAR data, to create our own raster, our own elevation models of these different units. I imported those into ArcScene because I thought it would look cool to see them mapped. They're all pretty flat. It's not a huge area. It doesn't have a lot of topography. So all the slides following this, if there's anything in ArcScene, it's going to be with a 5 times vertical exaggeration, just to get a better idea of what's going on, to see it more clearly. I mean, you can see in here, the red is higher elevations, green is lower elevations. And you can see there's kind of this regional trend kind of dipping down from east to west. So it gives us an idea of what's going on, but it's not exactly like to see maybe better. So what I did then is converted those polygons into lines with the polygon to line geoprocessing tool. And then from there, converted that line into points. And so this is just a Python script, and about an interval of every 500 meters took a point, and then from there we extracted values from those points. So each of those points now represents ideally the contact of that unit with the Cretaceous and the Devonian, or Cretaceous and the Mississippian. And now that we have these points with these Z values, or elevation data from the rasters, we can create a surface. So this is in the global polynomial interpolation tool. This is showing it now in ArcScene. This is with a third order polynomial. So you can kind of see a little bit more. There's something going on, but we want to see even more. I created this Kriging model to kind of map, interpolate between the points, and then I used that GPI to remove any kind of regional trend. So it's kind of dipping, kind of saw that dip in the middle, creating that, not quite an ellipsoid, but kind of two higher elevation surfaces. So remove those, and what you end up is something like this. So this is a very approximate reconstruction. It by all means, I don't think represents it exactly, but gives you an idea that there might be a little more going on in the subsurface. It's not just a flat plane between the two units. Things to take into account. So these edges of these, they can't triangulate out any further, so that kind of affects, what you end up getting. And because the Tuscaloosa is not pervasive everywhere, there's just certain spots that kind of create some artifacts in the interpolation, I think. So, and because the contacts are not, those lines aren't drawn on there directly, there's some offset on the DEM compared to what was drawn on the Alabama Geological Survey. It was difficult to put the points exactly along those contacts. So in the future, to do this again, probably expand the area and more accurately and precisely map that contact. So get a really good idea of what's going on between those two time periods, and maybe even map that paleotopography a little better. So here's some references. This is that 2017 paper that gave me kind of this idea. And then, of course, from the USGS and the Alabama Geological Survey, I was able to get some wonderful data. And that is it. Thank you.